Okay, so let's say you've made a bunch of repeat measurements and you've calculated the standard deviation of these to work out what the uncertainty is. And let's say it agrees with what you thought the uncertainty was by doing the propagation and looking at the measurements. So all is looking good. What you can now do is use the mean to get a more precise measurement. Now this only works if uncertainties are really random. But if they are random, and some points are randomly going to be high and some are randomly going to be low, then averaging a bunch of points will get you a more accurate measurement than any of the individual points. How much more accurate? Well, the average of n points is more accurate by a factor of root n. So if you take 4 points, root 4 is 2, so the average of 4 points is going to be twice as accurate as just a single point. If you had 16, root 16 is 4, so it's going to be 4 times more accurate, and so on. I've done some simulations to show this. What I've done is I've simulated lots of individual measurements, which are these green crosses in the plot. Now what I'm doing here is I'm averaging them 5 at a time. So this black circle is the average value of the first 5, this black circle is the average value of the next 5, and the next 5, and the next 5, and so on. And what you can see is that the original data points go from about -2.5 up to 2.5 or thereabouts. They cover a wide range, but the black circles, each of which is the average of 5 of the greens, they still have some scatter, but the scatter is much less. In fact, it'll be root 5 times less, which is what, 2 and a bit. Now, if instead of averaging every 5 points, we average every 20. So now this mark here is the average of the first 20 green crosses, this is the average of the next 20 green crosses, and so on. And what you can see is now, by the time you're averaging 20, the green crosses are still up from 2.5 to -2.5, but the black marks have a much narrower range. Most of them are within sort of about 0.3 to -0.3 with the occasional outlier. So averaging 20 has made things root 20 times better. And here, each black circle is the average of 50 individual measurements. So this point here is the average of all the 50 points that lie in this range, 50 green crosses. And now you can see they're all pretty close together. So, if you're trying to measure some parameter, what you normally do is you make repeat measurements and calculate the standard deviation to work out what the uncertainty is. Make sure it agrees with what you got by propagation. If it doesn't, think long and hard about why there's a discrepancy. But then you should average them all and work out what the uncertainty in your average number is by dividing the uncertainty of each individual thing, which you've just worked out, by root n. Now, when do you use the standard deviation of the mean as opposed to the standard deviation of the individual measurements? We'll come to this later in the course. Usually the standard deviation of your mean is telling you how accurate your mean is. And that's what you normally want to know. Let's say you want to measure as precisely as possible, I don't know, the number of birds flying over Mount Stromlo Observatory on a Tuesday afternoon. Then you should average over lots of Tuesday afternoons, and the most accurate measurement will be the average of all those individual measurements. But sometimes you need to know what the scatter of the individual is. So you can say, what are the odds on a given Tuesday afternoon you'll get more than 100 passing over? For that you care about the individual measurements. So they can both be useful at different occasions.